So, welcome back, everybody. This is the last talk for today, and our speaker is Shane Mansfield from the Sorbonne. And with his talk, we are back to the subject that we started out in the first session today, contextuality, and the title of his talk is Quantifying Quantum Advantage with Sequential Contextuality. Shane, please.
Okay, thanks a lot, Robert. Thanks to Shehan as well. It's great that this workshop is still taking place in spite of everything. It's fun to join Vancouver from so far away. Of course, I miss being there in person, but this is what we can do. So great. All right. So the talk today, it's going to pull together some things that I've been working on with various people over the last couple of years. So some of the work is with Pierre-Emmanuel Emeriau in Paris, with Mark Howard in Galway, and with Ellen Kashefi, who is usually in a superposition of being in Scotland and being in Paris. So let's see. All right, here we go. Okay, so just to give an outline of what I'll talk about, because I think it's helpful to have a picture of where we're going. I just want to start by situating the work I'm going to talk about within a sort of broader context of what I would call a foundational program for quantum computing. Then I'll give you some background on non-classicality and hidden variables. So this is something that may be familiar to some people, maybe not to all people. It's kind of the bread and butter of quantum foundations. So I'll just take a little tour through that to pick out some of the salient points. And I'll go on to this notion of sequential contextuality, which is what I really want to talk about. And I want to kind of finish by giving you two examples of where sequential contextuality is useful for quantifying advantage that we can get in computational or communication tasks. So that's the broad outline. Please interrupt me as I go along. These virtual talks can be disorienting for a speaker when you don't see an audience and have an idea of how it's going down. So interrupt anytime, I encourage it. All right. So this kind of broad context. So I would say that this work inscribes itself within a foundational program for quantum computing, where the objective is to try to understand what computational advantage can be afforded by using quantum resources. And so if you spend some time thinking about this, I think you probably agree with the point that I want to make here. If quantum systems are really able to provide advantages to us over just using classical devices, then the story must come down somewhere to a behavior of these quantum systems that would have been inaccessible to classical resources. Otherwise, we might just as well have used classical resources. So there must be something. And so here are some questions that as a community we begin to have some answers to. So you can ask, what are these non-classical behaviors? And a good answer seems to be contextuality, for example. Now, we might want to nuance that a little bit and put some caveats, or say there are some special kinds that are good and not. But okay, let's broadly say contextuality seems to be good. And we could ask, how do these behaviors, how does contextuality in particular relate to quantum advantage? And on this, we have some specific examples. And we start to have more and more examples, but we're not quite at the stage yet of having a full kind of systematic understanding. So that's probably a kind of a preview of where people are trying to get to. So to say a little more about where we might hope to get with this, one thing that would be nice to have that I'm kind of aiming towards myself in some of my collaborations, in particular with Samson Abramsky, Roy Suarez-Barbosa, Marty Karvonen, looking for kind of high-level reasoning about the contextuality that we have in our quantum resources and how we can manipulate it and spend it. So ultimately, the idea here is that we might be able to build a systematic and sort of structural path to exploiting quantum superiority, if we talk about the grail of quantum computing. Okay, so that's kind of the broad picture, but now let's start to zone in a little bit. So non-classical behaviors, first of all. All right, so we're scientists and we should be careful about when we talk about non-classical things in quantum mechanics. We often hear wild things in sort of general media. You get all sorts of strange and confused discussions of things like Schrödinger's cat and superpositions and parallel world lines and so on. If we're to be careful as scientists, the sensible way of talking about non-classical behaviors is via no-go theorems. And no-go theorems tell us that some particular behavior of a quantum system cannot possibly be simulated by a classical system, subject to some constraints that classical systems are supposed to have. So there are a bunch of these things. I put some of them here. So familiar ones to begin with: non-locality and contextuality. These are kind of established by some well-known theorems. This is not an exhaustive list. There are other theorems that follow these things, but just to give an idea. There are some other behaviors as well that maybe get discussed a little bit less in a computational context, but which I think should also be in the picture. So things like macro realism, as discussed by Leggett and Garg. Spekkens' generalized contextuality is something that's quite studied at the moment as a computational resource. And then we have this kind of strange result from Pusey, Barrett, and Rudolph from 2012, which says something about the nature of the quantum state. So we could perhaps talk about what behavior is going on there and what its use would be. Okay, but so what I want to do is I just want to start by talking about hidden variable models, which we can really think as a kind of language for discussing all of these different no-go theorems. And when we talk about hidden variables, the basic thing that we posit is the existence of some space of hidden variables. And then when we talk about the various components of our physical theory, let's say in quantum mechanics, our preparations, our transformations, and our measurements, we have hidden variable counterparts. So preparation of a system in some quantum state, if I'm trying to model this with hidden variables, then that's going to correspond to some probability distribution. So P here is probability distributions over the set lambda. So it's going to be some probability distribution on my hidden variables. Transformation is going to be some function on my hidden variables. Or a little more generally, we could talk about stochastic maps on them. As it happens, for what I want to talk about today, it's fine to talk about functions and we get generality for free, but let's not get too caught up on this for the moment. So here we could, if we want to talk about stochastic maps. And finally, measurement it's going to be just a function from your hidden variables. So if you know what hidden variable you are, then the measurement should be described by some, again, stochastic map to an outcome set. So give you some probability distribution over the outcomes that you expect to see. All right. Now, if our hidden variable model is a good one, it should reproduce the predictions of quantum mechanics. And how should it reproduce them? Well, as a weighted average over these ontic states of just what you expect. So we've got some probability of being in a particular state, and then we have the probability of that state, of arriving at any other state, if we're performing a transformation, and then we have the outcome distribution for whatever state we wind up in. So the no-go theorems, they arise when hidden variable models and the Born rule that we use in quantum mechanics to get our probabilistic predictions, when these things make differing predictions. And something that we should point out. Yes, go ahead, Robert.
I want to inject a question. I don't know if this was the right moment. I'm thinking back and forth whether I'll ask it, but measurement here. Mm-hmm. So what about sequential measurements? I mean, when you think of a measurement process, wouldn't you also want to include a state update?
That's true. So I'm not going to be talking about sequential measurements in this talk. So I don't have a need to really introduce that mechanism into the hidden variable models at the moment, but that is something that is considered, of course. That's the key thing in the work of Leggett and Garg, for example. That macro realism is really the idea that your measurements should not disturb the state that you're looking at. So, okay, yes, if you wanted a fuller kind of hidden variable model that could account for measurements in sequence, which I'm not going to talk about here, I'm going to talk about transformations in sequence, then yes, you might want to introduce some rule for
Outside's
how
good. Fine.
Things update or don't. Okay. All right. So as I was saying, no-go theorems arise when hidden variable models and the Born rule make differing predictions. So something that I should point out right away is that in order to get differing predictions, we're always going to require some additional structural assumptions, some constraints on our hidden variable models. Otherwise, quantum mechanics is a perfectly good hidden variable theory by itself. Okay, so let's talk about these things. I have maybe a slightly unusual perspective on contextuality. So bear with me, this is how I see contextuality. So I call it a structural perspective. So we have some basic components in any operational physical theory, these preparations, transformations, and measurements. Actually, we could pass to some sort of more categorical description where we could describe all of these things as being morphisms on system types. If this means nothing to you, ignore it, it doesn't matter. Okay, so we have these basic components, and what are our classical constraints? Well, we talk about contexts, and contexts are going to be any composition or combination of those basic components, for example, in a quantum circuit. And the constraints that we usually are talking about is that our hidden variable models should respect this kind of composition. And of course, when we get a component like a measurement that appears in different contexts, we ask that it's represented the same way in our classical hidden variable model. So I really see contextuality as being something structural. So we want a model that has the same circuit structure, the same topological structure as the context that we're trying to explain. So this maybe works better with an example. So let's talk about Bell and Kochen-Specker. So talk about their classical constraint. It's locality constraint, or if we want to talk about contextuality, it's a non-contextuality constraint. I mean, just to talk about locality. So kind of in a typical Bell type experiment, we might prepare some entangled state. So here I've started out with separable state, and I would put some operations on it just to entangle everything. And then I end up making some measurements. And so the idea would be that, I wonder, can I annotate actually? Maybe. Right, cool, okay. So that's not very nice, but so we have measurements here. And so the idea is that however this measurement is described in my hidden variable theory, it should be independent of the other measurements. It should be independent of these guys. Okay, so how do we say that a little bit more? Oh wow, you have to stop annotating to move forward or something. Okay, so in this case, a context is a set of compatible measurements. If we're talking about contextuality, compatible is just spatially separated if we're talking about locality. And we want that the ontological representations, so that the hidden variable representations of these measurements, they respect that compatibility. So they should be independent. So I'm talking about probability distributions here, and they should just factor. So they should just be product distributions. And of course, like I said, we want that the probabilistic behavior of a measurement is independent of which context it finds itself in. So independent of which other measurements are being made. So this is maybe not the most usual way to talk about kind of Bell, Kochen-Specker contextuality, but it's a perfectly sensible way to talk about it. It's equivalent to our usual definition. Okay. I'll give another example so we can kind of see the structural perspective. This example has to do with transformations. So another reason why I want to present it is so that we see that even though this has to do with transformations, it's a little bit different to what I'm going to call sequential contextuality next. Okay, so Spekkens had an example of what contextuality could mean for transformations. And in one of his examples, contexts are convex decompositions of a fixed transformation. So I have a fixed transformation and I have two unitary decompositions of it here. Now, if we want to make the kind of structural assumption that we expect from our hidden variables, if they're to obey classical constraints, it's that, well, we should respect these convex decompositions. So if I have a function or stochastic map to describe the transformation T, I should be able to describe it as the same convex combination of the stochastic maps for the UAs and the UBs and the UCs, etc. So I just expect these convex decompositions to be respected at the ontological level. And of course, I expect a context independence. So if UA appears in two different contexts, then it gets represented in hidden variable world the same way both times. Okay. So here we have kind of two examples, and now let me move on to talking about sequential contextuality. So we have the trick now, let's try a different kind of combination of systems. So I want to talk about sequences of transformations. So here we have a fixed preparation, a fixed measurement, but in between we have transformations that, okay, maybe we can control, we can substitute something in for something else, but ultimately we're just going to talk about one, or we're just going to talk about sequences of transformations. So a context is a sequence of transformations. The ontological or hidden variable representations, they should respect this sequential ordering. So if I want a map that describes the overall sequence, it should really factor as a sequence of maps, one for each of the individual transformations. Okay, and again, we're going to ask for context independence. So if I have two different sequences, I have a particular U that appears in both of them, I expect that the hidden variable model should represent it the same way both times. Okay, so since this is something that is less usually talked about than Bell locality or Kochen-Specker contextuality, I think it's useful just to give an idea of what it could mean if we had a violation of sequential non-contextuality. So what it would mean is that it rules out, sorry, there's a typo here. The model is obviously supposed to be a model. So what it means is that if we have contextuality in this sense, there's no hidden variable description possible where transformations correspond in a modular sort of composable way to what we're doing operationally. So I can't have a description of my transformation that is well defined independently of transformations I may have made before or transformations I may make later. So this is just as problematic as any of the other forms of non-classical behavior, I would argue at least. Okay. So let me push on. Don't forget to interrupt if I'm causing confusion at any point. Okay, so that's a notion of contextuality. It's the one I want to talk about. I also briefly want to say something about how to quantify contextuality. And so I'm going to use an old trick. So I'm going to first talk about the empirical behavior that I get from my protocols. So an empirical model I'm going to define as just being a a set of probability distributions, one for each context. So in this case, one for each sequence of transformations that I choose to make. And the probability distribution is going to be a distribution over the outcomes that I get for the fixed measurement. So this is really following the path of Abramsky and Brandenburger from the sheaf theoretic approach to contextuality. This kind of description as an empirical model. So let's just give an example. So here's a very basic sequence of operations. A and B can be control bits. So let's say when the control bit is 0, the transformation is going to be an identity, and when the control bit is 1, it's going to be a pi/4 rotation around the z-axis of the block sphere. All right, so then we have contexts. It's any combination of input values. And we have probability distributions at the end. So here I've assumed that the measurement is Pauli X, and you can work out what happens as an exercise if that feels, if that's a funny thing for you to do. But otherwise you can trust me that these are the probabilities that quantum mechanics would give. So these are probability distributions over the outcomes. In other words, it's just a set of probability distributions. So this is an empirical model for me. And now I'm going to talk about how to quantify contextuality in an empirical model. And so what I'm going to say first is that empirical models, they are closed under convex combinations. And this just comes from the fact that probability distributions are closed under convex combinations. So a thing that I can do is I can ask, well, if I have an empirical behavior, can I factor it into one part that is non-contextual and some leftover? So that's decompositions of the form I've written here. And we're looking in particular for decompositions where we maximize the weight omega given to the non-contextual behavior. So if we take a maximum over all such decompositions, we get the non-contextual fraction for E. So that's the amount of behavior that I can explain in a non-contextual way. And whatever is left over is the part that's irreducibly non-classical, and that's what we call the contextual fraction. So it's always going to be a number between 0 and 1. 0, if we're completely classical, everything can be explained non-contextually, and it's going to be 1, so that's the maximal value. It's what we call strong contextuality, to borrow again the term from the sheaf theoretic approach. Okay. So now we know the kind of non-classicality I want to talk about. We know how to quantify it. I'd like to talk about some of the examples where we can use it to quantify. So first example, and it's kind of harking back to where Bell, Kochen-Specker contextuality was seen to be useful in Robert's work, actually. So we're in the measurement-based quantum computing setting where we have a classical computer that can control a sort of flow of operations that's being performed on a quantum resource. So in particular, it's going to pick measurement settings. And when we make a measurement, we get a value back at each time. And so this is the kind of measurement-based scheme, a classical computer with access to a quantum resource. Okay, so the classical control computer, it is determining the sequence of measurements. And for the example that I want to talk about, we're going to make a sort of a toy limitation on it. And we're going to say that it can only perform Z2 linear computations. So it happens that when we give access to quantum resources, we can straightforwardly boost the computational power of this limited classical device so that it can do nonlinear computations as well. And so Robert had a result, so from 2013, those may have appeared earlier, where any L2 MBQC, so a measurement-based quantum computation of this kind, where we restrict the classical computer to Z2 linear computations, and where we make one operation at a time and receive one measurement as we go along. So one of these kinds of computation can deterministically compute a nonlinear function if the resource that we're interacting with is maximally contextual. And moreover, we can get a result about error. So if we want bounded error computations, we require just contextuality, maybe not maximal. So there was a slight sharpening of that result in a paper with Samson and Rui, where we used this contextual fraction measure to make a quantified statement about precisely what the error rate you can tolerate is, if the task is, so okay, the hardness of the task is going to be some measure of how nonlinear the function is, and we have a particular amount of contextuality. So it's a relationship between the error that we want to tolerate, the amount of contextuality we require, and how hard the function is that we're trying to compute. Okay, so it's interesting because it kind of allows us to make some resource sensitive reasoning. We can really look at a quantum resource and say, well, it's this contextual, I should be able to get this amount of advantage, am I making best use of it, and so on. Or if I want to have a better performance, I know something about the resources that I need in order to get there. Okay. All right, so that's talking about kind of the Bell, Kochen-Specker type of contextuality. So now I kind of go back a little bit in time to when I first started working with Elham Kashefi, and she had just been involved in this work with Dunjko and Kaprignotis, and so they had been looking at this kind of sequential protocol. And the curious thing about the protocol is it seemed to be doing like the very same thing from Robert's example that Robert was looking for. So it's boosting sort of a linear computer to being able to do nonlinear computations. So the classical control computer is just the same, just Z2 linear, and the quantum resource in this case is just a single qubit state with measurements performed on it in sequence. And if you do the protocol as I've described here, you can work out that the answer is deterministically the product of A and B, the input bits. Okay, so this is curious. It's doing the same thing. It's boosting computational power from just these linear Z2 linear computations, this Parity L complexity class, to being able to do full classical computing. But contextuality in the traditional sense, it can't arise in a single qubit. So this is known. And so the question arises, what, if anything, is the non-classical behavior here? And so it was from studying this example that I started to think about sequential contextuality. So let's talk about how we might model this with hidden variables. A first thing to say is that classical computers, they can very easily compute the product of two bits, A and B. This is not a problem for a classical machine. And a classical device that does this in itself constitutes a pretty reasonable hidden variable model. So we need to think about what's going on here. Of course, this idea of boosting computational power from Parity L to full classical computation really only makes sense if we're working in a computationally restricted regime. So what we should notice is that these Parity L circuits are built from NOTs and C-NOTs only. These are the only gates that you need. And we can try to push this constraint onto our hidden variable models. So this gives us a properly constrained hidden variable setting with which to analyze the problem. So now our hidden variables have precisely the amount of computational power that we want. Okay. If we push these constraints, that we only build circuits from NOTs and C-NOTs, we get, so maybe it's not so necessary to go through all of these things in great detail, but so the hidden variable space is just going to be a collection of bits. The transformations have, okay, a particular description. I'm supposing that that transformations commute, which is a feature of the protocols that that Dunjko, Kaprignotis, and Kashefi looked at. It greatly simplifies the general description of transformations and measurements. So, but anyway, you can take my word for it that this is how they look. So we've got some constraint on the kind of hidden variable models that I can have. And now I look at what it means to realize this computation of the product of the input bits A and B in such a hidden variable model. And I get these equations, which are basically just the empirical predictions, with the right-hand side filled in as the answer that I know I should have if the protocol performs correctly. Okay, this maybe looks a bit intimidating, but
Shane, I think there's a question.
Yes. Okay, let's go for it.
Okay, Siti, do you have a question? You need to unmute yourself. Okay, maybe there's no question. Okay, let's continue. Sorry for interrupting.
Okay, no problem. So if there is a question at any point, just hop in, please. Don't be shy. Okay, so let me jump back to where I was. So okay, if we suppose that the empirical or that the hidden variable model actually does what it's supposed to do, then we have these 4 equations. And these might look a bit intimidating, but it's actually very simple to reason about them. We can see that these are inconsistent constraints. The reason being that the right-hand side's clearly sum to something odd, while the left-hand side, if you look at this carefully, you'll notice that every single vector here appears an even number of times. So when I sum these things, everything cancels out modulo 2, and the left-hand side should be even. So I have a kind of a classic inconsistency. It's the Merman style argument for contextuality, although now it's for sequential contextuality. So if I can perform this computation that the Dunjko-Kapriotis-Keshefi protocol does, then I am necessarily sequentially contextual. In fact, I'm necessarily strongly sequentially contextual. All right, so what we ended up finding for such protocols, so we can generalize them as transformation-based computational protocols. So we have, again, a parity control computer. We have a fixed preparation, a fixed measurement, and we just control some commuting unitary operations along the way. And we can derive exactly the same quantifiable relationship that we found for Bell contextuality in the L2 measurement-based quantum computations. So here we have a relationship between sequential contextuality and one of the classic, I think I can say, examples of advantage from contextuality of the Bell, Kochen-Specker type. So yeah, okay, I should be careful just to say which kind of contextuality I mean each time. Okay. All right, so that's one example. And then I wanted to briefly say something about another example that I've been looking at recently with Pierre-Emmanuel Emerliao and Mark Howard. And so this has to do with advantage in information retrieval tasks in communication scenarios. So the kind of task that we're talking about, I'll give you the general definition afterwards. So the kind of task that we're talking about is where we have Alice has n inputs. She's given n inputs. She is allowed to transmit a message to Bob, which is going to be a single dit or a single qdit. And Bob gets asked one of m questions about the input and aims to output the correct answer with a high probability. So this is the kind of setting that we're in. It's an information retrieval task in a communication scenario. An example of this that is often talked about in quantum information is random access coding. So that's a special case where the task is to retrieve any one of the input dits that Alice had. So Alice sends a message to Bob, and Bob can be asked to return any one of the input dits. So it's an example that's much discussed in quantum information because it's well known that being able to send a Q dit gives an advantage over sending a Q or over sending a classical dit. So classic example for qubits, I think, is from Ambinus. I won't say the year because I'll surely get it wrong. Okay, so a more general description of an information task in an NMD communication scenario, so N being the number of input dits, M being the number of questions, and D, of course, being the dimension of the message that Alice is allowed to transmit. It is that we have a finite set of questions and that we have some set of winning relations. So for each question that could be answered, there is some winning relation that tells me these answers are the good ones that they need to be aiming to output. All right. So we had the Q-rack as a basic example. I'm going to give you a different kind of example, and this is what we dubbed the Torpedo game. Incidentally, the Torpedo game was presented at QPL a couple of weeks ago by Pierre Manuel, and I think that video is up on YouTube, and he goes through the Torpedo game in much more detail than I'm doing here, so that's well worth a look if these things interest you. All right, so we can think of the Torpedo game as a kind of pacifist alternative to the well-known game Battleship. And the ship here resides in an affine plane of dimension D. So affine plane, you should think about the top edge being stuck to the bottom edge and the right edge being stuck to the left edge. So if you wander off the plane to the right, you re-emerge on the left. And if you wander off the plane to the top, you re-emerge on the bottom. Okay, so this is the kind of geometry that we're working in. So the game goes as follows. Alice gets sent a position by her commander. She has to move to that position. She communicates with Bob, but she only communicates one dit or one Q dit. So the reason is that if it's intercepted, it doesn't give away her precise position. Bob is then asked by his commander to shoot a torpedo along a line of a given slope. And Bob, while he has to shoot with this given slope, he can choose which line of that fixed slope. So it could be shoot along a row and he chooses which row, or it could be shoot along a column and he chooses which column, or it could be shoot along a diagonal or an anti-diagonal and he chooses which one each time. And his goal is to choose one of the lines in order to minimize the risk of hitting Alice. Okay, so really the protocol, the strategy that Alice and Bob enact, it can be framed in this kind of information retrieval task setting. So Alice is given these two input dits. She's able to send a single dit or Q dit to Bob. And Bob gets asked to shoot his torpedo in one of the slopes, which, so I've labeled this set a bit strangely, but it's really from the geometric interpretation. So the labels here are supposed to be the slopes that Bob can be asked to shoot in. And we have a set of winning relations, which is basically just avoid Alice. So we can try to decipher that further, but the simple interpretation of that is avoid Alice. Okay. Of course, this is a relation, so it's not a function. There can be more than one good answer. So for instance, if Bob is asked to shoot along one of the columns, there are two columns that are going to avoid Alice in any instance. Okay. So what about classical strategies if we're limited to sending a dit? So classical strategies, it turns out the most general thing you can do is come up with some partition of the grid, the plane that you're living in, and you color it with D colors, where D is the message that you can send. So we had some fun thinking of these things as like disco dance floors and stuff. when we got, particularly when we got like d equals 5 solutions and things. So so that's it. Here is a strategy for the game. We can check computationally what the optimal classical strategy is. So for d equals 3, it's 11/12. That's the optimal classical strategy. For d equals 2, it's 3/4. So you can't have a perfect classical strategy, but you can do reasonably well, let's say. All right. On the other hand, you can get a perfect quantum strategy. So let me kind of briefly talk through this because it will give you an idea of how we concocted the game and where this comes from in case it seems arbitrary. So if we want to win the game, we want this kind of equation to hold. So the pi's in this equation, they correspond to mutually unbiased bases. So the lower subscript tells you which one of the mutually unbiased bases you're interested in dimension D in this case. So I'm talking about the dimension D strategy. So we have 4 mutually unbiased bases labeled infinity, 0, 1, and 2. And within each of these mobs, I have a number of projectors, and I'm indexing them with these superscripts. So in each mob, whatever state Alice sends, for each mob, one of the outcomes should be forbidden. That's basically how we get a perfect strategy. And so this actually makes the connection to some very useful machinery in quantum information. We can describe phase point operators in terms of mobs, in terms of sums of projectors of mobs. And this gives us an immediate connection to Gross's discrete Wigner function, which is defined in this way. And so the strategies that we looked at, the optimal quantum strategies, they happen to be maximally Wigner negative at Alice's position. So one thing is that we know that Wigner negativity relates to contextuality in a Bell, Kochen-Specker sense. This is from the work of Mark Howard previously and collaborators. All right, well, we're going to go for a different kind of take on this. We're going to try to analyze it sequentially. So here is our communication scenario. I'm just stretching everything out so that it's in good sequential form. So it turns out that we can always express our strategies in this way, where we have a fixed preparation, a fixed measurement, and all we do is enact some transformations ux, uz, and uq along the way, depending on the input bits that we get and the question that we're asked. If we want to model with a hidden variable model, we're just going to ask for a hidden variable model that respects the constraints of the problem. So it should be memory restricted. I should only be able to communicate a DIT. So D equals 3 case is going to be a probability vector in R3. Transformations. So here I'm moving to the stochastic picture. It can be any left stochastic matrix. So it's a transformation of probability vectors that preserves probability, if you like. And measurement, the most general thing that you can do is project onto one of the basis vectors here. So that's the kind of model that matches the problem we're looking at. And if the model realizes the empirical behavior, so here I've subscripted the empirical probability distribution with the input bits x and z and the question q, we should be able to reproduce that distribution as essentially I see, okay, so I should have written left stochastic matrix M. So forgive me, I have some scripts in here. So, okay, so these M's are the hidden variable representations of the transformation. So I should be able to describe my hidden variable model as a probability vector acted on by 3 stochastic matrices, left stochastic matrices in sequence. And if this is a good model, it should recover the empirical probability distribution. Okay. So then we get around to the result that relates sequential contextuality to advantage in the torpedo game. So the theorem actually goes a bit further. It says that for any information retrieval task expressible sequentially, like we've just expressed the torpedo game protocol, then we have this relationship, which is really just what we've seen before. So it relates error to the amount of contextuality, sequential contextuality in this case, and the hardness of the task. Hardness of the task here is expressed in terms of the omega c, which is the classical value of the game. So we get the same kind of theorem. I know some people like to think visually about this. So I have a little graph which kind of tells you what the feasible region is for a given amount of contextuality and a given error rate that you want to accept. So a corollary to this theorem is that to win the game deterministically for d equals 2 or d equals 3 requires, I mean, for any d actually, requires contextual fraction 1. So it requires maximal or strong contextuality. Okay, so that's all I wanted to say about that example. And I think at this point, I will try to slow down to a conclusion. So, right, so what I hope to have done a reasonable job of presenting. I can't tell if it was reasonable because I can't see how it's gone across to any audience members, but hopefully something went across. So hopefully you got the message that sequential contextuality, it's a natural way to think about non-classicality for operations performed in sequence, in series. Of course, as Robert pointed out, we might need to be a little bit more careful if we want to talk about measurements in series. We could do that, but for now, I'm really only talking about transformations. And sequential contextuality, it's useful in quantifying advantage in 2 examples. So to go right back to the beginning, I said we have a bunch of specific examples now where we can begin to tie contextuality to advantages. Of course, yes, we're still waiting for an overarching general systematic theory, but the more examples we have, the easier that should get. So here are these 2 examples. One is computation of nonlinear functions, and the other one has to do with the torpedo game and more generally information retrieval tasks. So I just want to make a final point that in both cases, I put additional constraints on the hidden variable models that we're looking at. So if you want to talk about sequential contextuality from a purely foundational perspective, and you want to just go out and do experiments to find out whether the world is sequentially contextual or not, maybe these are not the examples that you want to be looking at. These are not sensible constraints to put on a hidden variable theory of the world, of the universe, but they certainly are sensible constraints to put in place for the computational or communicational problems that we're looking at. All right, so that's pretty much everything I wanted to say. Thanks for listening, and thanks again to the organizers. I'll take any questions if anyone has them.
Yes, questions, please. Oh, there's a Q&A. There's stuff in the Q&A. Let's see.
Okay, so I'm not sure I can see that while I'm in full
so
screen.
there's
Actually.
plenty. So let's begin with Ernesto Galbao's question. So I'll read it, but Shane, maybe you go in the Q&A session so that you can read it for yourself.
Sure. So I may need to stop sharing the screen to see this. Otherwise, I don't see how to get there. But okay. I'll just hop back if I need to.
Properly.
Sure.
Ernesto writes, thanks for the nice talk, Shane. How does your sequential non-contextual models compare with finite state automata or models involving some limitation on memory size?
Ah, cool. Okay, nice question. I have not looked at that. I haven't thought a lot about that. They should compare, I mean, they should be quite similar, if not. I guess in finite state automata, a thing that we would have is actually what you mentioned, Robert, that you would be able to update the state as you go along. So that's one difference, but it's one thing that you might also want to include in the kinds of hidden variable models that we look at here. So that kind of reminds me of the sort of work on contextuality that Ottfried Göhne did with various collaborators on finite state machines. Yes, so a short talk, or a short answer, I don't have anything very interesting to say about that, but I think that should be a good connection to follow up.
So, good. Shane, can you now see those questions in
yes.
the Q&A?
In the Q&A, yes, I can see some.
So the next question is by Matty Hoban. I don't know how helpful it is if I read it. I presume everybody can read the questions. So maybe I just, Shane, I just send you to the Q&A questions box. So you have quite a few there to go through.
Okay, all right. So for Matty's question, okay, so he says that for the Torpedo game, he guesses that quantum strategies don't win perfectly. Yes, that's absolutely correct. They don't win perfectly, but they still give an advantage over the best classical strategy. If true, Matty says that a post-quantum theory could do better. That's true, and he asks if I've thought about what these theories might look like. I haven't really, no. So I guess what Matty's getting at is that you could have some sort of sequential analog of the PR box. Yes, so that's a good question. I don't have anything more to answer on that, except that I agree that's definitely interesting to look at too. More generally, is there an analogous principle to the no signaling principle? I'm not sure. I'm not sure there's something directly analogous. So maybe one principle that you could bring in. So I've kind of assumed that, okay, so the classical assumption for me is that the description of the transformation should not depend on anything that's happened before or after it, or that will happen after it. And I mean, we could take an approach to this, which kind of links with Ernesto's question as well. We could take an approach to this where we allow transformations that have happened previously to affect the current transformation, but we would want at all costs to avoid future transformations affecting the present one. So we could look at models like that. So with the memory restrictions, I do actually have an example of where we can't explain the empirical behavior by kind of forward propagation of influences through transformations. So maybe that's the kind of thing that could be analogous to no signaling, but then, okay, I don't know. So anyway, that example I should mention is with Pier Manuel Emeryau again and Ricardo Falero, he did an internship with me just a few months ago. So that's not written up yet, but that's an example that forbids this kind of forward propagating influence. Okay, I've slightly gone off topic there. I need questioners to like be pointing me back onto the right track, but let me try to move through. Oh wow, they really keep going. Okay, I should go faster. Do I think this result can shed light on quantum speed in general? Or can someone use quantum foundation theory to investigate quantum speed up? I see, right. So right through to quantum supremacy. Well, yeah, okay. So I'm talking about some examples of advantage. These are not examples, the kind of examples that typically get spoken about in the setting of quantum supremacy or quantum superiority, maybe is a more judiciously chosen word. Right, so I would love to think of a way where I could find a connection between sequential contextuality and maybe more heavy duty speed ups, but I don't have any insight onto that yet. Although there are quite a lot of protocols that do work with sequences of operations, so I feel that there is scope to investigate this. I guess the short answer to that is it's something that I should, or others should also investigate in the future. So good question. Then question from Ross, do I see any hope for contextual arguments for computational advantage in more realistic models? Yeah, well, so it seems to me that there is a good case for sequential contextuality being useful in memory restricted scenarios. So Parity L is maybe not quite a memory restriction. Of course, a special case of Parity L is where you just restrict yourself to a classical bit and your only operations are reversible operations, which is essentially the not operation or an identity operation. So it's, I mean, we could think of it as a kind of memory restricted setting. I think that in general, if we're to talk about memory restriction, sequential contextuality can be interesting, and we can say things about things that go beyond Parity L. So hopefully the Torpedo game gives a different case. That's maybe not quite a kind of computational example or a communication task. I see. Wow. Okay, so I'm not sure where to situate myself in this list anymore.
Matty Hoban, I think you just had Ross's question, now Matty Hoban again.
Okay, any comment on Ernesto? Oh, a comment on Ernesto's question. If I can decide things in Parity L, then this goes beyond regular languages. I don't know. Probably there are other people present here who could answer that better than I could. And another question from Matty. Matty is excited with the questions tonight. Is thus you go beyond DFAs. I'm not even sure what DFAs are actually. This may be my tired brain, but hop in with a response if that makes sense. Okay, Nicholas. Can one always combine sequential operations with the final measurement and essentially conclude that sequential contextuality is a form of measurement contextuality? Okay, that's a very good question. The answer is no. The answer is no. One way of seeing this is that, well, we don't have any right, so for measurement contextuality, you need non-trivial contexts of compatible measurements. So in particular, I need to be able to make several compatible measurements on my system at once. And in these protocols, you're only ever going to be able to make one measurement at a time. So we're not going to be able to explain this as measurement contextuality in any usual sense. Another way of seeing this is that we know that measurement contextuality, kind of the Kochen-Specker contextuality, does not manifest itself in single qubit systems. And yet, okay, when we put some additional constraints on our hidden variable theories, we see that sequential contextuality can be manifested there. So somehow it seems to stretch into a realm where measurement contextuality is not fully welcome. That's okay, that's a nice question. All right, let me hop on. So Lorenzo has a question. Have I tried, or is it possible to prove a no-go theorem for sequential transformation, non-contextual hidden variable models without further constraints and for quant
Shane,
theory? Okay,
could you read the questions fully? I think attendees cannot see the Q&As.
Sure. Okay. So Lorenzo asks, have I tried, or is it possible to prove a no-go theorem for sequential transformation non-contextual models without placing further constraints and relations on precise protocols, like the constraints that I have here on a memory restriction or the kind of computational power of the hidden variable models. So I have no example of that, and I suspect that without some sort of memory restriction, it won't be possible. So I'd think a little bit about this. I don't think that will be possible. So that's, I mean, you can ask if that's a problem. I think from a computational perspective, no, I don't think that's a problem because, well, memory constraints are always going to be relevant in computational settings. From a foundational perspective, it probably requires that we make, yes, some sort of additional ontological assumption about the size of our ontology and so on. But these are also things that have a history in foundations. So I think it still remains interesting there. But yeah, but my feeling for that is that it's not going to be possible to just prove a theorem without any additional constraints. Okay, and then Will Kirby. So I put a constraint on hidden variable models that their operations factorize in the same way as quantum operations, which he says seems quite natural. And then he asks, is there an analogous constraint for measurement or preparation contextuality? Or is it specific to sequential transformations only? Right, well, okay, so an answer to this is I can see all of these kinds of contextuality as existing somewhere in the structural picture. So the structural picture I gave of contextuality is that really you should have one form of contextuality for every kind of composition operation that you have operationally, or every kind of combination that you can have operationally. So if you want to talk about composing measurements in parallel, then you'd be talking about locality or non-locality. If you want to talk about composing things in sequence, it's going to be sequential contextuality. So I'm not sure which kind of measurement or preparation contextuality is meant here. So the kind that is often discussed in papers by Spekkens and collaborators has to do with stochastic decompositions of measurements and preparations, so similar to the stochastic decompositions that I showed for transformations. So yes, I think we can also see that in the same way, just where the kind of composition that we want to be respected is this kind of convex combinational structure. I hope that's a reasonable answer to that. Okay, I see. All right, cool. So I think I've come to the end of the questions from the chat. I'm sorry that I didn't read all the questions as I was going through them earlier on. Hopefully the answers gave a clue to what the questions were. I should have maybe known that before. Okay. I'm prepared to stop talking and boring people.
Good, okay. So let's ask for more questions. Okay, no, I mean, it's late. Europeans probably want to go to bed. Apologize, but maybe I can ask a question. It's a kind of an open-ended question, and the concrete end it has is this assumption. So I'm going back to your earlier example, the work with Elham Kashefi, and the concrete end of the question is maybe about this mod 2. The assumption of only mod 2 processing that is kind of hardwired, it appears, in the hidden variable model, although I'm not quite sure about it. So my question essentially is this. When I look at this example with the three unitaries in sequence, although I'm not sure you said it, but all signs point towards this being kind of the circuit model equivalence of Anders and Brown's 3-qubit MBQC employing Mermin's square.
Yes, exactly. Yes.
So a question that people asked a couple of years ago, and there was previously unsolved, is okay. Here if you look at the MBQC version of this, it is contextual. It's just a normal Kochen-Specker notion of contextuality. But if you transform it to the circuit model, it is a computation on a single qubit. So how can that be contextual? And it seems that you have put in this place, you have come up with a notion of contextuality that makes the circuit model, which is just on 1 qubit contextual. So that seems to be perfect fit, because we want kind of a computation to be contextual independent of which computational model you look at it in. So that's all good, but you no longer talk about Kochen-Specker contextuality. You're talking about a different model now, and I just want to know, how does it make you feel? So different notion of contextuality, and again, the only concrete end to my question is, you have this apparently this computational assumption hardwired into your model that there is a computational restriction for that hidden variable model. So maybe you can, it'd be nice if you could comment on that. How you uniformity across computational models.
Okay, yeah, that's a good point. So okay, so what I take from that is that, okay, now it seems nice that there's some answer where we still have contextuality as an explanation in this single qubit example, but it's no longer the more familiar kind of contextuality, and somehow this seems to be a shame. Well, okay, so I could say two things in response to that. So one is that it opens up an interesting line of questioning, which I don't have good answers to yet, but which is something to be considered. It is how we can transform one kind of contextuality into the other. And so maybe there's a way of just making these interchangeable forms of contextuality somehow. So that's a whole question that I would like to understand better. Another answer to this is that I don't feel, so, okay, obviously I'm quite attached to the Kochen-Specker notion of contextuality. I've done a lot of work on this stuff. I don't feel too upset that I've moved away from it, in a sense, because my sort of structural picture of how contextuality arises generally applies to both of these. So from the structural perspective, these are really just two particular forms of a more general notion of contextuality. The Spekkens notions also fall into that. So I think from this perspective, I see them all as being different manifestations of this kind of structural notion of contextuality, which also needs some development. So that's not a closed question either. Mm-hmm. I don't know if that's an answer that satisfies your curiosity, Robert.
Yeah, no, I think we can have follow-up questions later. But yeah, I'm satisfied. So thank you. So other questions from the audience? Okay, I don't hear anything. I don't see anything in the Q&A portion. So that concludes the workshop for today. I mean, the official part.